All right, let's talk about rational expressions and equations. Three terms in there which you should be able to wrap your heads around. Let's take them one by one. Rational. Rational means a fraction, something divided by something else. You're used to seeing rational numbers, any number that can be expressed as a ratio of two integers. Okay, we're going to take it a little bit further now. We're going to use all that information you know about polynomials and quadratics and factoring them, and we're going to mix it all together and see what we get out of it. Expressions. Well, expressions. What's an expression? Expressions are a statement of value. Think of it as a number with a variable attached to it, or a set of variables attached to it in different complex ways. So it's a quantity or an amount of something. And whenever you add an expression to another expression and you equate it together with an equal sign, you got something called an equation. So expressions are the things without the equal sign or without a less than or a greater than sign or some combination. And equations have that equal sign or some kind of relation between the two different expressions that you're looking at. So it could be this side is greater than or equal to that side. That would be an equation. So we're going to mix it up and take a look at a few different things here. Let us start by clearing our desk space here and continuing with Unit 4 of our workbook balloons on my page, on page 132 it says. And we're actually going to go to page 133 and take a look at what we got going on here. All right, so we're going to start off simply as usual, and we're going to look at a couple of equalities here and see what these things equal to. Now, we're going to do it in a slightly more seemingly complicated way. It's overkill for values like this, but it's a useful tool later on when you're dealing with more complicated polynomial expressions, okay? I mean, you know intuitively that 2/4 has the same value as 1/2. But I want you to understand that you get there by multiplying that 1 and by 2 by the same factor, okay? Now, you're used to dividing that by 2 and dividing that by 2, right, to simplify the fraction into its most simple form, and you'll get the exact same thing, right? But this is kind of important to see here, what you're doing, because when you look at these, those will divide out, or if you really want to anger the mathematical gods, you'll say they cancel out, but they're dividing out, leaving you the 1 over the 2, okay? And it gets a little bit more useful here, because if you're going to do this one without a calculator, you've got to think of common denominators. It's like doing a factor tree or factorization on the top and the bottom and seeing what you got. So, if I look at this, I see immediately that there's a factor of 7 in here. So it's 7 times something and 7 times something over there. Well, 7 times what gives you 56? Okay, that's pretty obvious, right? 7 times 8. Okay, and just because I've been working with numbers for a couple of days and a few months and stuff, I know that 7 times 14 is also 98. I mean, I just learned to recognize that. And the more you play around with numbers, the more you get comfortable with them, the easier that kind of thing will be to see, and it won't bug you too much. Now, I mean, the 7s divide out, of course, but we're not done. We can go a little bit further here, because there's factors hidden in the 8 and the 14, which will also help eliminate stuff. So if instead of the 8, I have 2, because I can divide 8 by 2, and instead of the 14, I'll divide it by 2 as well, and you ask yourself, what's going to be left? Well, I'm going to be left with a 4 on top, and I'm going to be left with a 7 on the bottom, right? Now, it's not immediately clear to me that 56 over 98 is 4 over 7, but when you do it step by step like this, you see the relationship a little bit better. So this is why it asks you to do it without a calculator. These are all expressions. Expressions, again, are just statements of quantity, and that quantity doesn't have to be a fixed quantity. It can be a quantity that changes depending on what the variable or variables are. So if there's no equal sign, then we're just looking at an amount. 2x over x minus 3. If x were equal to 1, in this case, then this expression would equal 2 over -2 or -1 in total, right? And so the value changes depending on the variable, the value of the variable. The point is that no matter what, and no matter how many variables you have, it always equates to a value, all right? So these are some different expressions you'll see, and as we move through the unit here, we're going to see about how we could simplify some of these to make them, well, make them simpler. So think back to when we were dealing with radical expressions and equations. There were two situations where certain x values were excluded from the mix. We called those restrictions, right? Restrictions on x or y or whatever the variable was. So the first case is when the radicand was equal to something that was less than 0. We could never have a radicand equaling less than 0. So if there was an x or an expression in a radicand, we did that inequality where we figure out what value of x would make the radicand equal something negative, and then that we counted that as a restriction from the expression or the equation. The other case where we looked at restrictions on x was when the x would make the denominator of a fraction equal to 0. Because once again, dividing any fraction, any number by 0 gives you an indeterminate form. It makes the expression blow up. It's just not allowed. So when we're dealing with rational expressions, we're interested, again, in values for x or y or whatever they are in the denominator that are not allowed. And values for x that would make the denominator equal to 0 are not allowed. And so we're going to start testing for those. And because it's a new unit, and why not, we're going to give them a new name. We're going to call them non-permissible values. With rational expressions, we have to find out what those non-permissible values are, and we have to state them, okay? So a non-permissible value is any value for a variable that makes the expression undefined or indeterminate, okay? And so we're worried about, of course, values of a radicand, which would be less than 0. But for the immediate future here, we're worried about values for x or y, which would make the denominator equal to 0. All right. So usually when you have a fraction of a over b, we say that a or b can be any member of the real number line, any number you can imagine, positive, negative, rational, irrational, it does not matter. But there's one value for b that is not allowed. It makes the value blow up, okay? It creates an undefined or indeterminate form, and that is when b is equal to 0. So when b equals to 0, the expression blows up. Therefore, b cannot be equal to 0. Okay? And that would be 0 would be the non-permissible value for x. Well, for this case, b. So how does that work in practice? Well, let's take a look at a couple of examples here. This is not a too terribly difficult little expression here, 7x over 8x plus 16. We are concerned only with the denominator so far. Okay, later on it gets a little bit more complicated, but for now, let's just look at the denominator. When the denominator is equal to 0, the expression blows up. It becomes undefined or indeterminate. So we must not let the denominator equal to 0. In other words, 8x plus 16 may not equal 0. So what value for x makes this so? Well, just a little bit of simple algebra does that. And then a little bit more of division here and there does that. And presto changeo, we have discovered a value for x that is not aligned. X can be any number in the real number plane here, except for negative 2. Because if it were negative 2, then the denominator would equal to 0, and the expression would become undefined. Well, let's take a look at the other side here. 3 over x cubed. Well, we're interested only in the denominator, values for x in which the denominator would equal 0. So what we would want, well, what we don't want is for x cubed to be equal to 0. Take the cube root of both sides. Boom. All right, let's move on and see if this thing gets a little bit more complicated. It does. We have something that looks a little bit more complicated here. Now, I want you to think back to why we make you deal with quadratics and factoring in the first place, something that started last year. Well, it's all in service of some higher power. I've told you that it's all in service of the calculus, learning this big idea called calculus in grade 12. So how is this going to help you? Well, by this point in your mathematical careers, you should be identifying x squared minus 25 as being having very special factors. It is, in fact, a difference of squares, isn't it? right? And you should also recognize the denominator, because this value is half of that value squared, right? Half of negative 10 is negative 5, negative 5 squared is positive, right? Do you recognize that? There's a perfect square trinomial, okay? Perfect square trinomial. And how does that factor out? Well, that's like this, right? It's x minus 5 quantity squared, or x minus 5 times x minus 5. Why is that useful? Because now you can get values for x directly from here, which you could not get here. Trial and error, perhaps, could help you find out what x squared minus 10x plus 25 equals 0. But that's messy. In fact, that's probably beyond most people's ability to do. But if we factor it, and if we also do a little bit of simplification there, x minus 5 divided by x minus 5 cancels out to threaten and imperil the mathematical gods. They divide out, they're 1. We get x plus 5 over x minus 5. And so now the expression we're looking for to look for our non-permissible values is simply x minus 5 not equal to 0. To put it another way, x must not equal to positive 5. Because if it does, then the denominator equals 0, you get an undefined or indeterminate form, and the expression blows up. So x can be any value whatsoever except for negative 5. Now, this factoring here is kind of helpful. You don't need to factor the numerator in this case, but let's say we flip this on its side. Let's say that instead of x squared minus 25, we had x squared minus 10x plus 25 over x squared minus 25 on the bottom. Would we get a different answer? Would we get a different answer? And I'm going to submit to you that we just might. We just might. How would this work out? Well, instead of x minus 5 quantity squared on the bottom, you get x minus 5 quantity squared on the top. And on the bottom, you would get x minus 5 times x plus 5. Okay? And so you might get the same kind of dividing out, but if you left it in this form, could x be equal to positive 5? Well, if x were equal to positive 5, then this would be 0, and 0 times this would also be 0, and so you get a 0 denominator, and that wouldn't work. But you'd have also x not allowed to be negative 5. So in this case, that. Now, we got this from this form here, but I think if you look at the x squared minus 25, you get the same idea, right? Because you get x squared cannot be equal to 25, and when you take the square root of both sides, that square root principle comes into effect, where x equals plus or minus 5, right? And so we're just showing you how that works here. And you get a different answer depending on which side you flip it. Kind of cool. Well, let's take a look at this one here. Now we have two variables, and so we have to figure out what values of x and what values of y are not permissible. Well, I'll tell you one thing. You know that this whole bottom expression may not equal to 0. X minus y may not equal to 0. And when you do some algebraic magic here, you simply get that. Any values for x and y are good, unless they're equal. That's your non-permissible value. The two values where one value where the two variables are the same value. Easy peasy lemon squeezy. All right, let's move on to doing some simplifying now. Now we've got the idea of non-permissible values. Like simplifying radicals, you're going to have to simplify and then state your NPVs. Just like in radicals, you simplified and you stated your restrictions. Same thing, two parts to every question. So remember at the beginning of my talk here, I talked about how there was a complicated way to deal with numerators and denominators, and then you show the dividing out. Well, we're going to start putting it to use here. Here's an expression, and this expression is equal to, if I rearrange, we're going to keep the negative there, but if we look at the 21 and the 35, I hope you see a factor of 7 in there, and I hope you also see a factor of x. So 7x is going to be a common factor both on the top and on the bottom. So on the top, you're going to be left with, what, 3? And on the bottom, you're going to be left with, what, 5x cubed, right? So I've just done a little bit of factoring of the top expression, 21x. 21x equals 3 times 7x. And on the bottom, 35x to the 4th equals 7x times 5x cubed. Easy peasy lemon squeezy. The 7x's divide out. Or if you really want to tick off the mathematical gods, you'll say they canceled out. They're really dividing out, right? Because 7x divided by 7x equals una. All right? And so what's our next step here? Well, we're left with a negative still. And we have 3 over 5x cubed. That's what we got. So there's your simplified expression. Cool. Any restrictions? Any non-permissible values? Well, what value of x would make the denominator equal to 0? The only value I see for x would be 0 itself. So x may not be equal to 0. There's your NPV. The simplified expression and the non-permissible value. So moving to this example now, you see and you can imagine that there's a couple of quadratics here, a couple of x squareds. You've got to imagine that they're there for a reason, and you'll learn how to factor quadratics and polynomials for a reason. So let's use our factoring skills and let's see if we can't figure this out. So this whole mess here, let's look at the top. X squared plus x minus 12. The numbers 4 and 3, because 4 times 3 gives you 12, and the difference between 4 and 3 is a 1. So there's probably going to be, what, an x plus 4 times x minus 3. Let's see if that works. There's your x squared minus 3x plus 4x. There's your positive x. Negative 3 times positive 4 is negative. There we go. I factored x squared plus x minus 12. You see, you'll learn the factoring of the quadratics for a reason, because they're always going to come back at you. 2x squared plus 7x minus 4. Use your factoring technique of choice. There's a couple. You can do the cross here, right, where the two values on the top. You need a product that comes to 8, but a sum that goes to plus 7. Okay, you can do it that way, and then you do the decomposition. As you get better here, you're going to know, well, I mean, you know that there's going to be a 2x and an x, and you come to figure out that, or you come to learn to identify the factors pretty easy when you've done these long enough. I know just by inspection that we've got a negative 1 plus 4 in there. Now let's make sure it works. There's your 2x squared. 4x minus x is positive 7x. Good. And then negative 1 times 4 is negative 4. Good. We got it. And now take a look what happens. Yeah, that's what we want. That's why we factor. So you can simplify and divide out unnecessary terms. Okay, I believe that that is the simplified term. Cool. Now, just like radicals, you've got the simplified answer, but you also have to state, well, for radicals, your restrictions. For rationals, your non-permissible values. So your first one is right there. 2x minus 1 may not equal to 0. Let's do a little bit of algebra there. 2x may not equal to 1. X may not equal to 1/2. Okay? Makes sense. If x equals to 1/2, then this part in this expression here would be 0, and the expression would blow up. Good. But there's another. You have to look at all different forms of the expression, because this equals this equals this. And so look at that term right there. Whoops. X plus 4 may not equal to 0 either, because if x equals, or well, let's just finish this off. x may not equal to negative 4, because if x does equal to negative 4, then you get a 0 in this expression, which is perfectly valid. It's not simplified, but it's a perfectly valid expression of this value. If x equals negative 4, you get a 0 times whatever this, it doesn't even matter what this is. 0 times anything is 0, and your expression would become undefined because of that version of the expression. So you get two NPVs. X may not equal to negative 4 or 1/2. All right? All right. I think it's time for a little bit of fun. Let's have some mathematical, rational fun here. Page 135. 135. We're going to get a little bit more tricky here. Remember that the goal is to simplify. And you simplify by factoring. Factoring and then dividing out. If you really want to tick off the math gods, they'll say you're canceling out, but you're really just dividing out, creating ones, making things look simpler. You might be able to factor the top, you might be able to factor the bottom, or you may even be able to factor both. So how do we approach an expression like this? Well, with creativity, which is why you're learning math. You're learning math to build those creative abilities inside your brain to let you problem solve stuff. Well, straight off, I see that there is a factor of 2 in the numerator, right? I can divide 2 out of 2x and get an x, and I can divide 2 out of negative 6 to get a negative 3. That's pretty obvious. I hope you see it. Of course you do. I'm going to do something really funky here, which is less obvious, and I'm going to show you how I derive it on the side here. But I'm going to rearrange the 3 minus x, and I'm going to make it to negative x minus 3. Whoa, what have I done there? Well, let's do a sidebar here. Let's figure stuff out. What is 3 minus x? Well, it's the same as negative x plus 3. Do you agree? Just switching the terms around. Okay? So if I have negative x plus 3, what if I divide out a negative 1 from this expression here? Okay. Well, if I take negative 1 out of negative x, I'm going to be left with x. And if I take negative 1 out of positive 3, I'm going to be left with negative 3. And so this is the same as negative x minus 3. Ah, magic. So that's how I got this, by doing this. Now, how are you going to know to do this? Well, when you do the simple factoring, we're going to rely on you to recognize that this sort of looks like this, and that you think that you have to rearrange this somehow to divide out, right? And so this is where the creative thinking comes out. It's something you will not get immediately. You have to practice it to be able to see it. And soon you'll learn to recognize stuff like this. All of this to say the x minus 3 terms will divide out, and I will get negative 2 over 1 as a final answer or final expression of this. And wow, does that really work? Well, it does. There is your final simplified expression. It just seems that 2x minus 6 over 3 minus x equals negative 2. Now we got to worry about those non-permissible values. Well, it equals negative 2, but it doesn't always equal negative 2. It only equals negative 2 when x is a certain value. Well, we have to look down here. We have to look at the x minus 3. Okay, so for non-permissible values, the denominator, no matter what form of the equation you have, we'll look at this one, we can look at this one, it doesn't matter. So let's take this one here. 3 minus x must not equal to 0. In other words, 3 must not equal to positive x. In other words, x must not equal to 3. There's your non-permissible value. It's as simple as that. It works here. Well, we got it from here, so it definitely works here, but it also works here. If x is equal to 3, 3 minus 3 is 0. Negative 0 is still 0. So this restriction or this non-permissible value works in both of these forms here. Okay? So you're looking for values of x in any version of the expression that you have. Are we getting the hang of this? You know that you're going to have to do some factoring. The more of this you do, the more of this it's going to be easier to be able to factor complex trinomials like that, okay? You know one term is going to be a 3x, and you know the other term is going to be it's just going to be an x all by itself. I know that because one's positive and one's negative, I know that, well, they're going to add up to negative numbers, but they're going to multiply to give me a positive. So I know that they're both negative. And again, the more you do this, the more it'll become really clear that it's 3x minus 2 times x minus 2. Let's double check, right? 3x squared minus 6x minus another 2, there's minus 8x plus 4. Yes, good. 6x squared minus 4x. Well, there's a polynomial, there's a quadratic, but the only thing we can do to factor, I mean, you can complete the square if you want to be really silly about it, but we can easily pull out a 2x, can't we? And we got that. Except that that first term here will be 3x. Little oopsie there, okay? And let's just double check, make sure 2x times 6x is 6x squared, minus 2 times 4 is 4x. Good, minus 4x. And so what do we got? Well, hey, look at the 3x minus 2, divide out. That's what we want, okay? So our simplified expression will be x minus 2 on the top and 2x on the bottom. That's our simplified expression. Our non-permissible values are values for x here or here or here, which would make the equation, which would make the expression, excuse me, blow up. We can't do much here because, you know, there's lots of values, but this tells the tale here. If x equals 0, then the expression blows up because 2 times 0 is 0 times this is still 0. So x cannot be equal to 0. And, well, if x equals 0 as well here, it would make this part of the expression blow up. But we also have to look at over here, the 3x minus 2. 3x minus 2 must not equal to 0. In other words, 3x must not equal to 2, which means that x must not equal to 2/3. So my two non-permissible values are 0. Non-permissible values of x are 0 and 2/3. All right, how we doing? Ready to keep going? No? Okay, good. We'll do it anyways. All right. Well, you know that there's some factoring going on here. You know it. You know you got two things here. See, for me, when I look at complex trinomials, I know there's going to be a 2x and an x term. I know that. All right? But if you wanted to simplify your life a little bit first, the first thing you'll actually do is look for common factors just up there. And I'm going to leave this here because we can come back and take a look at where it goes. But I can do this as well on the top, can't I? Yep, I can pull out the 2. This 2 would come from here, and you know, we go backwards and see what this expression would be compared to this one. But let's do it this way here. It's a bit simpler. Can I do anything with the 3x? No, I can't do the same thing there. So I know I'm going to have a 3x and an x. And I know because this is negative and this is positive that they're both going to be negative because the last term that gives us the constant, negative times the negative, will be the positive, yeah? And so, again, you just learn to recognize there's going to be a 3 and a 1. I mean, you might accidentally put the 3 here, accidentally, and then the 1 over here. And if you work it out, you'll see that it doesn't come out. And then you know you just have to switch them. No biggie. But here as well, you can see where, oh, let's do up here. Let's do the top part. All right. 2 x squared minus 5x plus 6. Easy peasy, right? Negative 2, negative 3 are my values. Right? There's 5x, 2x, and 3x. The 5x, negative, negative is positive 6, good. And 3x minus 1 and x minus 3. All right? So what would this term here be? This would be what? 2x minus 6 and x minus 2. And it would be the same thing, right? But if you did it this way, you'd see that you have one more factorization to do here. You have to pull the 2 out of there to fully simplify. All right, we've come this far. What else can we do? Well, look, those 2 can go, and we would be left with 2 times x minus 2 over 3x minus 1. There's your simplified expression right there. What are my non-permissible values? Now, you don't have to go through that belabored process of going something like 3x minus 1 cannot equal to 0, therefore 3x may not equal to 1, which means x may not equal to 1/3. You don't always have to do that. It's good for you to help organize. Soon you'll be able to do it by just inspection, just by looking at it. X may not equal to 1/3. And if you look at this value here, or this part of the term here, x may not equal positive 3 either. In both cases, it makes the denominator 0, and it makes the expression undefined or indeterminate. All right, last one. Well, it might not be immediately apparent where to begin, but I know that x squared minus 16 is a difference of squares, and I know what a difference of squares looks like. Yeah? And this might help you figure this out here. So do you see anything up here? We got an x, negative x minus 4. Well, is that not the same as positive x 5? Where'd the 5 come from? Plus 4, but times negative 1? Sure it is, because negative times x would be negative x. Negative times positive 4 would be negative 4. And then I can do some division combination of dividing out and eliminating or canceling division. Okay, I can do some dividing out. And so now I'm left with negative 1 over x minus 4. Okay. There's my simplified expression. My non-permissible values, well, x may not equal to 4, of course, from here. But nor can x equal negative 4. Here's positive 4. Positive 4 minus 4 would be 0. 0 times this is 0. But if x were negative 4, then this part of the expression would be equal to 0. So x may not equal to positive or negative 4. Those are my 2 non-permissible values. I was going to say that, my friends, is how you deal with simplifying rational expressions. Easy peasy, lemon squeezy. Go attack the practice problems now, starting on page 136. Cheers. Happy mathing.